Hi, welcome to Hashtag Math. We are going to derive inverse functions now. There are two methods. One is a formula we're going to derive here, and the other one is using implicit differentiation straight from the definition of the inverse. To find the formula for the inverse, we start by the definition. The composition of f with its inverse is the identity function. That means that when you compose f inverse, and apply it to x, you get back x. And now we see this as a composition of functions. So we're going to derive f of f inverse of x, and that is x. We are going to derive both sides of the equation and use the chain rule. We derive the outer function and keep the inner function inside, and then multiply by the derivative of the inner function, which is the derivative of the inverse function. So we are looking for that, the derivative of the inverse function. And since we have a multiplication, we can divide both sides by the derivative of f evaluated in the inverse. In this way, we obtain the formula. The derivative of the inverse function at x is 1 over the derivative of f evaluated in the inverse function. And this is our formula. Not always easy to apply this formula. Sometimes it is better to use implicit differentiation. And let me give you first an example using the formula, and then we're going to find the inverse using implicit differentiation. Here we have an example of two inverse functions. X squared and square root of x are inverses. So we can find the derivative of the square root of x by knowing the derivative of x squared using the formula. According to the formula, the derivative of the inverse function, in this case it's going to be the derivative of root x, at x is 1 over the derivative of f evaluated at the inverse function. The derivative of f is just 2x, so this is going to be 1 over the derivative of f, which is 2, and keep f inverse inside, and this is just 1 over 2 square root of x. And we already know that derivative, right? Great, that's how you find the derivative of the inverse using the formula. So we are going to apply the formula to find the derivative of ln x. If f of x equals e to the x, then the inverse of x is ln x, as we know. So the derivative of the inverse, that means the derivative of ln x, equals 1 over the derivative of f. What's the derivative of f? E to the x, right? So the derivative of f evaluated at the inverse function, which is ln x. And we get that the derivative of ln x is just what? 1 over, what's e to the ln x? Just x. So the derivative of ln x is 1 over x. So we did it using the formula. Now we are going to do it using implicit differentiation. Y equals ln x if and only if e to the y equals x. So we derive here implicitly d dx of e to the y equals d dx of x. E to the y is a composition because y is a function of x. So we derive implicitly. The derivative of the outer function is e to the y, and then we attach dy dx. And the derivative of x is just 1. And we just solve for dy dx. We divide both sides by e to the y, and we get that dy dx equals 1 over e to the y. And so dy dx equals 1 over x, because e to the y is just x. And dy dx is nothing but the derivative with respect to x of ln x, because y is ln x. So again, we found that the derivative of ln x is 1 over x. Let's do now an example where we use the derivative of ln and the chain rule. When we derive y, we notice that this is a composition. The inside or the inner function is 3x plus 2, and the outer function is ln. So we derive the outer function. Derivative of ln x is 1 over x. So this is 1 over, and you keep the inner function, 1 over 3x plus 2. And then we derive the inner function, which we know is 3. So the derivative of this function is 3 over 3x plus 2. Easy. In this example, we have a combination of functions. We have multiplication, we have a power, and ln x. What is the operation that joins my entire expression? Yep, multiplication. Here we have a multiplication. So the first thing we have to do is apply the product rule. So the derivative of y is keep x and derive ln x squared. So we derive it plus derive x and keep ln x squared. So we keep the x there, and the derivative of ln x squared is a chain rule again. Here's the outer function and ln x is the inner function. So we derive the outer function. This is going to be then 2, keep ln x and derive ln x plus the derivative of x is 1, and this is just ln x squared. And now let's put the 2 in the front. This is 2x ln x, and the derivative of ln x is 1 over x. This x is cancelled out, and the answer is 2 ln x plus ln x squared. Not bad, huh? Our last example for the video. First thing you have to do is what? See what's the operation relating the entire function. So here we have a quotient. So we apply the quotient rule. The derivative of y is going to be low d high minus high d low square the bottom, and away we go. This is 1 plus ln x. The derivative of ln, 1 over x, minus ln x. The derivative of 1 plus ln x is again 1 over x, because the derivative of 1 is 0, over 1 plus ln x squared. And then we can distribute the 1 over x, and we get 1 over x plus ln x over x minus ln x over x over 1 plus ln x squared. And these guys cancel out. And what we have here is a complex fraction. It's 1 over x over 1 plus ln x squared, which has a 1 in the denominator. So we keep the top and multiply by the reciprocal of the denominator. So the derivative of y. So the derivative of y is 1 over x times 1 plus ln x squared. Thank you.